And now we are going into our next talk, bringing, hi Faye.
Hiya.
This is Faye Claybrook, PhD researcher at Loughborough University. And she's going to talk to us about elastomeric structures replicate form for diabetic shoes. So when you're ready, well, we're gonna give it, yeah, when you're ready, yes, if you want to come on, I'm gonna come off.
My presentation was here and now we can't find it. There it is. Sorry about that little technical glitch. Okay, so hi. My work is on the use of additive manufactured elastomeric structures for diabetic foot management, which is basically the use of 3D printing and self-supporting structures for insole manufacturing. So I'm trying to make squishy material that can go in the shoe to withstand the different pressure ranges of the foot. So I thought I should tell you a little bit about myself and my background and the current research that I'm undertaking. So I'm from Loughborough University, which is, if you look at England and think of the middle, I'm somewhere there. And if you want to know a bit more, if you know where Birmingham is, I'm up to the right. So I'm a PhD researcher in the design school at Loughborough University, and I'm part of the digital fabrication group, whose research focuses on the development of additive manufacturing workflows and products to optimize the current processes available. So what I mean by the current processes is that how do we take something from ideation through to the final product, so from start to finish with the design that we want. So the products that we focus on are the customization of medical aids, such as insoles, arm splints, and armor, where multiple variations of additive manufacturing and 3D printing machines have been developed and designed for this new wave of 3D printing. So my background education-wise has always been at Loughborough, where I've done all my academic studies, and I'm an industrial designer that has specialised in 3D printing since my interest in the sector and my experiences and exposure in other workplaces. So the current research I undertake is in relation to diabetic management, where I am looking to adopt malleable materials alongside high-strength structures to withstand the load of the foot. So the characteristics of triply periodic minimal surface structures, which you can see at the top of the screen in blue, are surfaces with zero mean curvature and minimal areas within the structure with the same boundaries. So the replication of the structure's cell creates a porous material with high interconnectivity and strengthening adopted from nature. Examples of these structures in nature can be things like butterfly wings, beetles, and sea urchins. So if you look at them in a microscopic level, you're bound to see a TPMS structure there. So these high surface to volume ratio structures need exploration and consideration to the processing and materials that could be optimized for diabetic foot, because they have a high strength to weight ratio, so they could be put into the everyday insole. So if you look at TPU material alongside this, it creates a malleable approach for FDMM printing that can be tedious but could be beneficial to cushioning aids. There is limited research with the link of both TPMS and TPU materials to create these aids, due to it being difficult to control the flexible materials, which consist of a lot of a failure until you get this specification created. So as you see at the bottom of the screen, there's loads of failed 3D prints on top of a MakerBot, and then at the end, they're all successful. So sort of that process, which we've all been through. So the strut thickness in these structures is one of the most influential factors in the TPMS scaffold. So varying the weight of this can vary what the weight of the structure can withhold. So this independent variable could influence the pressure ranges alongside the TPU that's chosen for optimization for advanced applications of cushioning and safety and aids for foams that are currently on the market. Further interest in my work is also into anatomical scanning and optimal data while keeping low cost and easy onboarding if they were to be adopted into medical sectors such as the NHS or anything. Similarly, the pressure data of patients being informative to the insole manufacturing process. So what is diabetic foot? The disease is most often categorized into type 1 and type 2, where type 1 of diabetes is the lack and inability to produce insulin, and type 2 is the body responding badly to the insulin that's produced and can't be energized by the glucose that's there in the body. So diabetic foot costs England healthcare more than cancer treatments combined. And if we look into this, there could be the possibility to save £250 million in the UK. Type 2 is more susceptible to diabetic foot due to their lifestyle choices, and a pre-perceived lack of self-care amongst type 2 diabetics can cause this condition, which is solidified by the increase in ulceration without professional help due to the COVID-19 outbreak, which was reported as 3.9 million people in the UK. So this tends to be men over the age of 50 with high BMI and exposure to diabetes for 13 years plus. An increase in primary care and adaptation of a fast track pathway is needed. So if we can prevent the first ulcer, we could hopefully lower any skin complications and trauma that comes alongside with this. So what is diabetic foot? So there's peak ranges that emerge on the plantar surface of the foot, which is indicated in red on the photo on the left. So the plantar surface is the bottom surface of the foot. This can develop hard skin, calluses and ulcers and chronic wounds that diabetic patients are susceptible to. And once this happens, they have the inability to recover because there is too much glucose at the surface area. So how do these cause issues? The skin is damaged once an ulcer has developed, even after it's healed. However, healing can be difficult due to the imbalanced phases. The high glucose perturbs inflammation and increases infection, which is a major impediment. And due to this, the white blood cells are impaired for the necessarily remodeling of the dermal layers and the structural framework of the granulated tissue, and it's all hindered. Similarly, the pro-inflammatory and anti-inflammatory are out of ratio, so it gets stuck in a cycle and not being able to heal properly because the ratios have changed. Therefore, the need for preliminary stages in diabetic foot is required. The preliminary stages need to be taken seriously, as one of the plantar tissue has altered and minor lesions and calluses start forming. There's a strong risk of reoccurrence starting the cycle anew. If the insoles are manufactured to the feet as a preventative technique, as soon as the pressure ranges of diabetic patients start to increase, this could limit the first ulcer. So an indication of early diabetic foot ulcers is temperature. The foot heats up before it breaks down due to inflammation. So therefore, this early recognition of local temperatures could be used to inform the insole manufacturing alongside the pressure ranges. There is difficulties adjusting stiffness of insoles. So the foams can be manufactured and cut down to the size of regions, and even can be specified to each bit of the foot by cutting into blocks and sticking them together for CNC manufacturing. But this can cause a lot of waste, labor and time for machining doing this process, as it's a subtractive technique. So this indicates where additive manufacturing could come in. And if we use additive manufacturing, this could also improve ergonomic issues, where patients have indicated that arches are being too intrusive due to the redistribution of weight, and they find it difficult to wear them. So if you use your hand as an example, the top and bottom of your hand is hard, the middle is soft, and imagine something constantly pressing into it. It's really uncomfortable, and there wouldn't be a high ratio of people wearing these because it wouldn't feel comfortable enough to continue, even if it was helping them. So from all this information, it led to my first study, which was the investigation of additive manufactured split-P TPMS elastomeric structures for diabetic foot insoles, where initially only split-P was used as the TPMS structure. The project objectives were to better understand the material benefits of the TPU and the use of diabetic foot insoles, to study how this flexural behaviour can change due to the porosity that we choose and the strip thickness, and then understand how we can make an applicable workflow to design these insoles. So to understand the applicable workflow, we need to look at the current methods that are being used. So vacuum forming and subtractive manufacturing are the traditional techniques used for insole manufacturing for diabetic foot and for insoles in general, for things such as gait, collapsed arch, and flat feet. The latter, additive manufacturing, has improved these limitations of these processes and show a clear route for the future exploration of customized insoles. Subtractive manufacturing is the capture of the foot through digital fabrication. To obtain an anatomical representation of the foot, 3D scanners are used to transpose into computer-aided design CAD softwares. Then the generation of surfaces are made to match the plantar surface of the foot to create the insole. Then the CAD file will be sent to the CNC machine and manufactured out of the foam blocks using the subtractive manufacturing techniques everyone is used to, cutting away undesired material and leaving the finished insole. The foam, as I previously said, can be made with different densities and cut to the different regions, and these can be aligned prior to the CNCing by adhering them together and joining them, or they can be made afterwards by adhering and joining them together, depending on the setup of the certain place. So additive manufacturing is from a ground-up approach with the adding of material layer by layer to create the desired product. Manufacturers can start from minute detail in the millimeter range and can feature complex geometry that subtractive methods wouldn't be able to do with the tooling that they have. So the filament is deposited in successive layers from the 3D model on the computer under set guidelines with the slicing software to create the 3D print. It's possible to build any shape and material, and even combination of materials with this method. And additive manufacturing can be exploited for this insole manufacturing through the varying porosity, flexibility, and absorption of pressure exposed on the plantar surface of the foot. So this digital workflow would create a more detailed approach to the manufacturing process that is required for the intricate pressure ranges of the foot. The data can be collected, and then the correct structure can be chosen to withstand the pressure range that is susceptible to that diabetic foot and that patient. This can then be implemented into an insole and then customized to the patient in the exact way that they need to, in the exact way that the structures are tested in this study, just to the shape of the foot rather than the standardized side that was needed. So the process would go through the same steps with the CAD and the 3D printing, but rather than the structure, it would be the desired insole. So further research into optimal scanning techniques available at a low cost will be explored at a later date to further this process of research, but currently I'm just looking at the TPMS structure and the different porosities to focus on how these can adapt for the different pressure ranges of the foot. So this has been shown in a proof of concept insole that you will see shortly at the end of this presentation to show the intricacy in the results section. So given that there is limited investigation of elastomeric formed TPMS structures, in this preliminary study, the split P TPMS structure was chosen, and the resulting compressive properties with varying porosity using the TPU and the FDM additive manufacturing fabrication, we can create an image of the capabilities of what this can do. So the TPMS structures are a new approach for the replacement of this medical grade foam, and there is only one other study by Holmes et al. 2022 that tested the gyroid structure, and they reported that if they change the internal porosity of these structures, that the mechanical loading conditions can be tailored to match the compressive properties of foams that are currently on the market used for diabetic foot insoles. So for this study, each sample was compressed under the uniaxial loading machine to see the stress strain the structure could withstand, and therefore the pressure ranges of the structure before permanent deformation. So the ASTM D69515 standards were followed, where each porosity had 5 repetitions to find the averages and the anomalies. And similarly, the height was kept at 30 millimeter and 15 millimeter diameter for a 2-to-1 ratio and compressed at a strain rate of 1 millimeter per minute due to the required examining of these structures. So elastomers have complex mechanical properties from their deformable nature adopted by the material. Typically, more rigid materials will begin to deform with a linear profile before at a critical point the strain begins to increase for a near constant stress, which is a characteristic yield point of a material. This is a typical point of densification for compressed scaffold structures, whereby effectively all design porosity is removed from the structure. So however, for elastomeric scaffolds, yielding does not occur and the scaffolds are able to return to their original form as long as there's no hysteresis in the structure. So in the present study, to compare the compressive properties between these elastomeric scaffolds that were designed, we defined the maximum compressive stress. So a point where the porous test structure began to collapse while permanent dense deformation was absent. So in a rigid material, it would go linear, collapse, plateau, densification, or it would snap and break. Whereas in this material, due to the air being collapsed out of the structure, I'm defining it between the linear behavior and the collapse plateau. So if you made a little triangle, that's going to be where the maximum compressive stress is. So it doesn't go into the densification, getting rid of all of the designed gaps and air out of the structure, because then it would just base off the solid material. Hopefully that makes sense. So what I found was that there was a clear correlation between the porosity and the maximum compressive stress, whereby the increased porosity, there was a lower measured maximum compressive stress. So this was also reflected in the calculations for the compressive modulus, the Young's modulus, which imply a reduction in stiffness for increased porosity. It was noted that the calculated error for the structures with increased porosity for both maximum compressive stress and the compressive modulus. So the increase in the error values could be attributed to the unpredictable nature of the buckling and twisting and how the material is deposited of these structures, or there could be slight deviation in the interlayer adhesion, which could lead to unpredictability in how the structures deform when under a compressive load. So if we link this back to the study that was done by Holmes et al., it was found that the gyroid TPMS structure that they tested was comparable to the split P that was used in this study. The gyroid structure had approximately 0.125 MPa at 10% strain, and comparatively, the split P in this study was found to have 0.2 to 0.3 MPa, which is twice the compressive stress loading capacity. And comparing both of these to the compressive properties of typical medical grade foams on the market, the compressive strength of the medical grade foams on the market can cover 0.175 to 0.35 MPa. Therefore, the compressive stress of the TPU split P used in this study is within the ranges of the compressive stress found in clinically utilized foam materials on the market. And then even if we wanted to take this further, we could reduce the cell size and the strut thicknesses to get an even wider range of data. The compressive properties can then be tailored regionally to give an insole. So in theory, this can be adjusted and tailored to the unique loading characteristics of the individual. This showcases the use of a smart insole whereby pressure ranges can be adjusted to key contact points of the foot. So this is rather a crude model of a foot insole, saying there's only 4 main regions. However, the regions of the foot could be divided further into more intricate detailing. So you could have 10 different regions of the foot with different structures that were required. And you could even have it for each metatarsal head if that is what you desired. So the structure can be easily merged as the pattern, the baseline is the same, and it's only the porosity, meaning there wouldn't be a weak point within the insole because they have the same basic guideline, creating a watertight structure. So the use of scanning and pressure data can be measured in the initial data collection from patients and compared to the collected pressure ranges of each of these structures before the maximum compressive stress. Then the use of the plastic plateau before the maximum compressive stress is great for energy absorption as the porosity is compressed and released after impact, allowing the energy to be stored within the structures and keeping under the foot while being able to withstand the repetitive load of the foot when walking to actual physical continuous movement. So the future work that is going to be carried forward is to conduct this testing of the proposed insole by physically manufacturing it, examining the use of scanning data for customization of pressure regions in the real world context, and to understand the effect of hysteresis on the insoles from repetitive high pressure exposure. So further research has been taken. So the future steps that I've taken forward through additive manufacturing is the tuning of flexible materials for other uses of TPMS structures. So I've also looked at gyroid, diamond, and Schwartz. And the further use of TPU material, I've tested 2 different short hardnesses to understand the different pressure ranges and scope that this can hold and the capabilities of what this material can do. So the generic TPU 90A Shore is what was used with the split P TPMS structure and was used in this study once again. And then another hardness of 60A TPU was used, which is an extremely malleable material for FDMM printing and is quite difficult to get the parameters for the loading capabilities initially. Also, a wider range of strut thicknesses were chosen to create a bigger database, which could be worked on to input pressure ranges and output the correct porosity for the patient's specific needs. I thought I would show an image just in case people were confused by what I meant by porosity in the relation to strut thickness. So you can see as the strut thickness of a TPMS structure gets wider, the holes and gaps that are designed in them get smaller. So this could possibly influence the collapsing of these arches and the loading capacity. Then the analysing of this data is still being managed to ensure that the correct guidelines and the eventual database that will be formed from these structures is going to be reliable and able to be replicated into an insole from the pressures that the structures were capable to withstand on the uniaxial loading machine. So the compression samples for this study were taken the exact same as the split P structures, but instead of 5 samples for each, 7 samples were made. And the initial plan was to do this for both TPUs, but due to 60A being so malleable, there was a lot of pressure buildup in the nozzle, so that had to go to a 0.8 millimeter nozzle rather than the standardized 0.4, and could only replicate the larger strut thicknesses, so the 3 on the right, so the less porosity, so the 1.6 millimeter to 2.4 millimeter strut thicknesses. So overall, there was the 5 different porosities for 90A TPU and 3 porosities for 60A TPU. And the 2 different materials with 7 replications each, which equals 105 samples for the 90A and 63 samples for the 60A TPU. And the current information I can tell you is the overall characteristics of these samples acted the same as the split P, where the higher the porosity, the reduction in compressive modulus and the maximum compressive modulus, which you would expect from the previous study and the design of them.
Thank you, Faye.
That's currently
this is
what I'm doing.
That is fascinating. Thank you very much. That is an incredible insight. And I've got a few questions waiting for you here.
Okay.
Yes, and we're having a round of applause as well, digital applause. So there's a question about what kind of materials are you using in the research of the challenges that you face?
What is the challenges with the materials?
Yes.
So with 90A, originally there was a lot of fine tuning. So with the use of TPU materials, especially, there's a lot of stringing between depositing from one side of the bed to another side of the bed. So it was a lot of honing in on how to reduce the stringing that was capable. So reducing the speed, the travel speed, the wall speed, everything, but mostly controlling it in the CAD software beforehand. So rather than controlling it in, let's say, Prusa Slicer, for example, I controlled it in Entopology, so made no infills or anything. So I had a lot more control of exactly how fast the structures and where it would deposit the material. And the 60A was a lot more complicated because there was a lot of bending and buckling while loading. So I had to create a customized 3D printed gap. So it was a triangle funnel for the material rather than a parallel channel. So once it caught, it was squished and it wouldn't wind and bend and break and all of that. But most printers have a designed capability for that and loading gears at the front. It was just the one that I'm currently using I had to create the funnel for.
I see. We've got a question about testing. Are you testing for cyclical loading, since this is for insoles? And have you done life cycle testing or for a number of kilometers of usage? for the insoles?
So that's currently what I'm looking into. So I'm currently setting up a process to do repetitive loading on it over a certain amount of distance, or even over the average steps that people use daily, especially to that age range, gender and lifestyle choices. So being able for it to withstand that. So I'm going to do that in a mechanical testing way. And then also hopefully at one point I will take it into actual use with patients. So it's able to test the one against the other, and hopefully there won't be too many unexpected surprises, but there probably will be. Yeah. So.
Okay. Are you comparing different cell designs and orientation?
So from the different orientation, I haven't tested different orientations. I kept it in the like generic one that's been given, because there's quite a few papers out there that say there's minimal difference between the different orientations when you're printing. And for the different cell sizes, I kept them all at 10 millimeter cell size. So I was able to control one independent variable. So rather than having a wide spread of data that was loads of different cells, loads of different porosities, I started small with keeping the cell size at a size that you'd be able to see a difference looking at it, and then changing all of the different porosities. And then eventually I'll go into different cell sizes as well to make it further and further and further.
There you go. Are you looking at various widths of feet, adjusting the width of the insole for the customer?
Yeah, so different widths of feet in the sense that I'll be scanning different people's feet. So it'll go for the different geometries of the foot, dependent on what shoe size you are. So there isn't any exclusion at the end. The only possible thing that might be a problem is the size of my print bed. So if someone's foot is bigger than the size of the print bed that I have, then it could influence, and it could create errors if you were to split the insole in half, because then there'd be a weak point, a shear point within the insole. So that would be something that, due to my research, I'd maybe have to limit, but in a real life scenario, you'd create a bed that was big enough for any size foot. So that's something that I might have to take into consideration.
Well, these are life-changing products for the patients, aren't they? So they must. How quickly do you think we can see this happening as a common, as a common occurrence that will be incorporated for patients?
From my contacts and people that I know, they're very heavily wanting to be able to get the workload off of themselves for all of the specialized skills and individuals that need to be for inner sole manufacturing, especially the lead times. So the lead time of an insole can be 2 weeks to 2 months, whereas if we made it through 3D printing and put a sterile FDMM printer in a medical space, it could take from 2 hours to 20 hours. So it's a very quick lead time. And if it was able to use a database that meant it was easy for the clinicians and they don't have to learn a new skill, then that would save time as well. I've sort of lost where my question was and I've gone on a tangent. What was it? How fast it will go in. But yeah, it's hard to make the adoption into medical sectors because everyone seems willing and everyone seems happy to adopt, and they're excited about research and all the potentials of additive manufacturing. But sometimes I feel people are stuck in the ways that they do it and how they've done it this way for 20 years. So why would they change it? And they find it more of a workload. So it's trying to advertise that and then getting it through initial pilot testing and making sure that it is safe for diabetic patients and then nothing's going to be intrusive or cause any more damage to the environment.
Sure. I've got here, it says cell orientation can make a difference. 45-degree rotation can make a difference. I don't know if that's the person that asked the question earlier.
So I was looking, when I originally looked at cell orientation, I was looking at more like 90-degree difference. So 45 degree has certain attributes and qualities to it, but when you look at 3D printing, I think you can change. There's so many things that you can do with 3D printing that you could change every part of it and be like, well, what if I did this? What if I did that? What if I did that? So I had to look at the larger scope and be like, okay, so if we keep it to one independent variable and then we move it to more and more and more and more, then we can create a massive database that people can use. But we have to start small, or otherwise there'll be too many complications, overwhelming,
too many options.
Exactly. So it's definitely something in the future, because you could move it to any degree between 0 and 90, but if you moved it in 90, there isn't that much. So I was like, I'll keep it in one orientation and then I'll move it into the next.
Wonderful. Well, thank you